Okay, hello again. This is the video on chapter 6. I'm going to try to maybe have 3 videos on this chapter. This is the first one, and we're going to talk about, let me show you, talk about these sections here, most probably, maybe these two. Then I'm going to have another video for these two, and then another one for the rest of chapter 6. Okay, so let's get started. So one video on 6.1, 6.2, and one on 6.3, 6.4, and the rest of it another video. All right, so let us start. So what I'm going to do, I'm going to start actually by doing problems, and then I'm going to talk about concepts as we need them to solve problems. Okay, so let me open up some problems from chapter 6, starting with 6.1, and this is our calendar, of course. See, that's the calendar. So let us start with section 6.1, and the first problem I want to do is number 9. But before we do these problems, before I do any of these problems, I'm going to talk about the concept of exponential functions. So to do that, I need a little space here, so let me grab a wide area so I can work with it. So here you go. This is our whiteboard. Let's see. There you go. So what do we mean by exponential functions? Well, exponential functions are, first of all, related to, let's do some scratch work, related to this operation. Now, this operation is an operation that is called exponentiation. Exponentiation. So what am I doing to 2 and 3? I'm exponentiating 2 and 3. Now, I'm using this number as base and that number as exponent or exponent. So the way it works is that we write the base exponent number of times and then multiply. That's the idea of exponentiation. Now, every exponentiation, every operation has an inverse. For example, if I take 2 and add 3 to it, I get 5. Then what do I do to 5 to get the 2 back, right? And that, of course, is subtracting 3. So adding 3 and subtracting 3 are inverses. They cancel each other. Same is true for multiplication. Let's say I take 5, 2, and multiply it by 3. I get 6. So what do I do to 6 to get my 2 back? Well, I have to divide by what? By 3. So multiplying by 3, dividing by 3 are inverses, right? All right. And also notice here that you don't have to, if you start with 3 and add 2 to it, right? You get 5. Then obviously, in order to get the 3 back, you do 5 minus 2. All right. So that's the idea of operations and their inverses. Now, we are talking about this operation, which is exponentiation. So 2 to the 3rd power is 8. First of all, if I ask you to exponentiate 2 and 3, that's not the only choice you have. You could also do 3 to the 2nd power, which is 9. This time 3 is base and 2 is, so this time 3 is the base and 2 is the exponent. So now suppose I start with 2, you give me 2, and I raise it to third power, I get 8. Now you say, okay, I want my 2 back. What do I do to 8 to get your 2 back? Well, that is cube root. Cube root of 8 equals to what? Equals to 2. So this operation of taking third root of a number is the inverse of what? Taking a number and raising it to a third power. Now, what if you give me 3 and I do this to it? And you come back, you say, okay, I want my 3 back. What do I do to 8 to get the 3 back? Well, obviously, I have to reverse the operation, right, to give you the 3 back. What is that operation that I have to reverse? Well, that operation is taking a number, 3 in the exponent, and using a base and exponentiating. Now, the inverse of that operation, it is just defined just like that. So we're going to define it this way. First of all, it has a name. It's called log of 8 with the base of 2. So that operation that gives us the exponent back is called log base 2 of 8. So when we write log base 2 of 8, we're really asking a question. What is the exponent of this number that gives me this number? So what number do I raise this base to get this number? So that means the answer, of course, is 3. Why? Because 2 to the third power is 8, right? 2 to the third power is 8. So that's the idea of this chapter. This chapter is all about this operation and its inverse, right? Of course, we can have different bases, and we're going to talk about that. And we're going to talk about logarithm much more later. But for now, that's the idea. So let's talk about this idea of logarithm and practice a little bit before we get into exponentiation and exponential functions. So let me give you a few more examples of logarithm, and then we're going to do some examples. So, for example, if I say, what is log base 2 of 4? Well, you say 2. Not because 2 times 2 is 4, because 2 to the second power is 4. If I say, what is log base 3 of 9? Of course, you say 2, because 3 to the second power is 9. Now, the bases here could be maybe 10, right? So what is log base 10 of 100? Well, it's 2, because 10 to the second power is 100. Now, the question now is, what kind of bases can we use? And the answer is next. So now let's go back to this idea of exponentiation. So what we like to do is we like to create a function that has what? That has a base, right? Let's call that base b, right? And then we want to raise it to an exponent. So this is an exponential function. And notice that the variable is in the exponent position and the base is a number, right? Now, what kind of numbers should be used for the base? Well, here is the number line. Now, can we use 0 for the base? Well, let's look at an example. For example, 0 to the second power, what is 0? But if I set it equal to 0 to the third power, well, these two values are the same, but the exponents are not the same. So if we use 0, then this function would not be 1 to 1, right? So we cannot say that if the bases are the same, then the exponents have to be the same. So we're going to, and also 0 to x is just 0, so you just get a horizontal line that is not really anything interesting. So 0 we're going to exclude. So what we do, we put a little circle here is empty. That means no circle, no 0. Now what about 1? Well, 1 does the same thing. You see, it creates the same problem. So what do? We're going to get rid of 1 too. We don't want 1. Now what about negative numbers? Well, negative numbers create even bigger problem, because if I have, like, let's say negative 4 to x, well, if x is even, that would be a positive number. If x is odd, this would be a negative number. And then if x is a fraction, for example, let's say x is 1/2. Well, we know this would mean what? This would mean that this is square root, right? The 1 goes here and 2 goes here, right? And that is not a real number. So many problems. So we're going to get rid of completely, get rid of what? Negative numbers. And what we are going to do, say we only want numbers between 0 and 1, and the numbers after 1. So when we define our exponential functions, we're going to define them in two families. One family, b can be greater than 1, so we say b can be greater than 1. And another family, b can be between 0 and 1, right? So that's the idea. So let's look at some examples of these exponential functions. So let's look at some examples. For example, f of x equals to 2 to x. That's an exponential function. A member of the other family, f of x equals to 1/2 to the x power, right? And another example of this, a celebrity member, 10 to x. That's a celebrity member. And this one doesn't have a celebrity member. Maybe 1/10 to the x, or maybe 0.12 to x. All of these are what? Are exponential functions, and these are exponential functions. So another celebrity member here is the number e. I'm going to talk about the number e, but for now, e is a number, 2.718 is an irrational number, but that's a famous base, okay? So these are exponential functions. Now, to understand them, we're going to graph these later, but for now, we are going to, right now, go back to, we are going to leave here and go to our problems here, and I have to make this a little bit bigger so we can see it. That's good enough. So what we want to do, we want to go to, let's say, number 9, right? So what is number 9 saying? Well, number 9 saying, here it says, for the following exercise, consider this scenario. For each year, t, the population of a forest trees is represented by the function that. In a neighboring forest, the population of the same type of tree is represented by this. Round your answer to the whole number. It says, which forest population is growing at a faster rate? Now, so to answer this question, I'm going to talk about this idea of exponential functions. So if you start with certain number, let's say you start with 3, that's your initial amount, right? Now, if you keep multiplying by 2, what do you get? You get series of numbers like that, right? So basically, if you want to know what the value of f of x is, you start with certain number, let's say 3, and then you keep multiplying it by 2. So you multiply by 2, you get the next number. You multiply by 2, you get the next number, right? You get the next one and the next one. Now, so if you think about it, if you let x be the exponent, so when x is 0, right, then you have the original 1. If x is 1, then you get this number. If x is 2, you get this number, and so forth. Of course, this is only working with integers, but you don't have to work with only integers. So the power doesn't have to be just 1, 2, 3, 4, 5. It could be any number. But you can think of it the same way, because basically what you're getting is a proportion of the original number, right? It's a proportion of the original number. So you see 6 is 2 times the original number. That means you're multiplying it by 2. So you're adding 100% of it to it, right? So the numbers grow like this. That's called exponential growth, like that one. And if you start with certain number, let's say you start with 10, and keep multiplying by 1/2, right? So what do you get? Well, you keep getting what? You keep getting a smaller and a smaller numbers. And that would be of this kind of exponential. But this is not exponential growth, but this is exponential decay. So what happens, you start with some number and keep multiplying what? By 1/2, and you raise it to x power. So when x is 0, you just start with the initial amount. If x is 1, then you get the next one, and so forth. All right. So this number right here, if it is less than 1, looks like the numbers are going to go down. And if this base is greater than 1, the numbers look like it's going to go up, right? The numbers go up. All right. Now, if instead of 2, if I put a 3 here, well, now I have to keep multiplying by 3 instead of 2. So this number would be, so here this number would be 9, and then would be 27, and so forth. So they get bigger and bigger. So that means this shape is going to be sharper, right? So the bigger the base, the sharper the increase is going to be, right? So that's the idea. So if it's a positive number greater than 1, the bigger it is, the sharper the increase is going to be, right? So now that we know this, let's go back to this problem and talk about it. So one of these is, let me get this, I can write on it. So notice that this forest, right, grows like this. So the population of the forest trees is represented like that, and the other one looks like this, right? Now, which one of these grows faster? What looks like is this one is going to grow faster because this number base is bigger than that number, right? So this one grows faster. So which forest population is growing at a faster rate? This one. So think about this. You'll keep multiplying by what? 1.029, right? So that grows faster than that one. It says, which forest had a greater number of trees initially? Now, initially, that's when t equals to 0. If t equals to 0, a number to the 0th power is 1, so you just get 115. If t equals to 0 here, a number to the 0th power is 1, you get 82. So this forest starts with a bigger, larger number of trees than this one, Okay? Now, the next problem is assuming the population growth models continue to represent the growth of the forest, is which forest will have a greater number of trees after 20 years? So to do that, we basically have to do what? We have to take A of 20 and compare it to B of 20. Now A of 20 would be, when we put 20 here, we can use a calculator to do that. So A of 20 is 115 times what? Times parentheses 1.025 to the power of what? 20, and that would be like 188.44. And then B is what? B is 82, and then you just put parentheses, means time, right? And then is 1.029 to the power of what? 20. So that's 145.25. Now, which one has more trees after 20 years? Well, A, but we said this is growing faster. But it is true, this is growing faster, and it's starting with what? A smaller number of trees. This one growing is slower, but starting with larger number of trees. So it's going to take some time for this to catch up, right? So 20 years is not enough for it to catch up. But if you go later, let's say at 40 years, then you're going to see. So let me get the calculator back. So what I'm going to do, I'm going to get the entry back. Let me get the first entry back. So instead of 20, I'm going to put 40. So after 40, right, the one with 115, A, so A of 40 is going to be what? 308 something, 0.7, 0.8. And what about B? Let me get the B back. So what I'm going to do, I'm going to press second entry so I could get entry that I want back. Second, and then entry, second entry, second entry. That's the one that I want. So what I want to change that to 40. And you see it's 257. So B of 40 is actually 257. What does that mean? That means that B, right, A has 308 after 40 years, and B has what? 257. It's still not exactly more, right? But what if we go to 100 years? In 100 years, B of 100 is 1,430 approximately. And what is A of 100? That's 100. Well, let me get the entry back. See what A of 100 is. 100, it would be what? 1358. 1358. What does that mean? That means B caught up already. It's like 100 more approximately. All right, so that's how exponential functions actually grow. So let's do a few more. Let's do 14 to 17. It says, for the following, determine whether the equation represents exponential growth, exponential decay, or neither. Now, let's go look at 14. Is that exponential? Right? Well, what do we say? What does it look like? Exponential growth looks like what? Exponential growth looks like a number to a variable, not a variable to a number, right? That's not exponential growth. So if you look at these, so let me look at all four of them at the same time. This one right here, it doesn't look like a number to a variable. It looks like a variable to a number. So that's not exponential, right? So not exponential. Now what about this one? Well, this one does look like exponential because it's the base to a variable. So this one is exponential. And it's exponential growth because this number is greater than 1. What about this one? Well, no, this one is not exponential because x in the numerator, x in the exponent has to be by itself, not in the denominator. We have to have x here, but not this way. This is like 1 over x in the exponent. So that's not exponential growth or decay, none of them. So this one, not that. Okay, and what about the last one? This one, yes it is, and it's exponential decay because this base is what? Is less than 1. So that means you start with this and keep multiplying by this number. Well, you get a smaller and smaller values, right? All right, so that's the idea of those numbers. And let's do a few more. Let's do number 18 and 20. It says, use the following exercise. Find a formula for an exponential function that passes through 2 points. So let's do this one. Let's do 18. So in general, the exponential function looks like this. Let's say f of x equals to some b to some power, but then there is a initial value coefficient, which is the initial value here, right? So that's initial value. Okay, now we have 2 points. We are told that when x is 0, then when x is 0, y is 6. So that means when f of x is 6, x is 0. But b to 0th power is 1, so that's 1 times a, which is a. So a is 6. So we know the function is supposed to look like f of x equals to 6b to x. But we don't know what b is. But let's use the other point right here. When x is 3, y is 750. So 750 equals to, now we know what a is 6, and then times b to what power? To 3, right? You see right here it says when x is 3, y is 750. So we're going to divide 750 divided by, we're going to divide 750 by 6. 750 divided by 6 is 125. And b to the third, so b is going to be cube root of 125, right? Which is 5, of course. So the function we're looking for is 6 and then times 5 to x power, right? So that's the function we're looking for. All right, let's do another one. I'm going to do number maybe 20. So in this case, what we are given, we are given when x is -1, y is 3/2, and when x is 3, y is what? 24. Again, we start with what? F of x equals to a b to x, right? And then say, okay, when f of x is 3/2, which is y, see f of x is the same as y, right? And then a b to -1. Now a b to -1 means a over b, right? Because b to -1 means 1 over b. Actually, let me write it this way. So that means 3/2 equals to A times 1 over B. 1 over B. That means 3/2 equals to A over B. And then if you cross multiply, it means 3B equals to 2A, right? Or we can write that, B equals to 2/3 A, or the other way around, doesn't matter. We can write A is 3/2 B, right? All right, now that's one thing. That doesn't give us A or B, but it gives us a relation between A and B. Now, what about the other point? Well, let's work with that. When y is 24, then x is what? X is 3, right? So it means what? It means that B, it means that, it means that 24 equals to what? A times B to the third. But we know what A is. A is 3/2 B and times B to the third. So that means 3 times B to the fourth over 2 equals to 24. That means what? That means 3b to the fourth equals to 48, and b to the fourth equals to 48 divided by 3. So b to the fourth equals to what? What's 48 divided by 3 is 16. So b is going to, we know b is positive, so b is 4th root of 16. That means what's the number we write 4 times and multiply to get what? To get 16? That's 2. So b is 2. So our function is what? Well, we know b is 2, so our function is f of x equals to a, we don't know, but we know b is 2. B is 2, so let's write it like this. And what is a? Well, we know a is related to b like this. So if we know b, we know a. So a is going to be 3/2 times b. The 2 goes away. 2 go away, we get 3. So our a is 3, right? So we got 3 times 2 to x. That's the exponential function. Okay, now let's do 2 more. Let's do 20. So here it says, for the following, determine whether the table could represent a function that is linear, exponential, or neither. Now, if you have an exponential situation, remember I said in exponential, if you start with a number, right? If you keep multiplying it by a number, let's say greater than 1, you're going to end up being, multiply by 2, you get 6, multiply by 2 again, 12, by 2 again. So in order to find that number that you multiply by to get this, you just divide this. 6 divided by 3 is 2. 12 divided by 6 is 2. 24 divided by 12 is 2. So if we divide these values and we get the same number, it looks like this is exponential. It could be exponential growth or decay. So this number that we find could be greater than 1 or smaller than 1. But it could be, that would be exponential. Do we have an exponential situation here? Well, no, because if you divide, you don't get the same number. 40 divided by 70 is not the same as 10 divided by 40. Now, linear is when we take the differences and the differences are the same. So what's What's 40 minus 70? Negative 30. What's 10 minus 40? Negative 30. What's negative 20 minus 10? Negative 30. So this one is a linear growth. It's not exponential. So you start with a certain number and keep subtracting, right? 30. You're not multiplying, right? Now what about this one? Well, this one we can divide and see. So let's use a calculator to get the decimals. So if I divide 49 by 70, I get what? 0.7. What's 34.3 divided by 49? 0.7. What's 24.01 divided by 34.3? 0.7. So it looks like this one is exponential decay. This right here is exponential and is decay because it's decreasing. All right, so that's how we figure out whether it is linear exponential or neither. So can it be neither? Well, yeah, it could be neither. Let's say, for example, this one. Now, we look at the differences are not the same, and we divide them, we don't get the same thing. So it's not exponential or linear. So it's neither in this one, right? Because when you divide, you see, you get what? Different answers. It's not the same number. See that? These numbers are not the same. And when you subtract, they're not the same. So it's not linear or exponential. All right, let's do a few more. What about number 28? Well, to do number 28, we need to talk a little about compound interest. Compound interest is the application of exponential functions. I'm sure you've heard of compound interest. Basically, the idea is this. First of all, if it's not compound interest, it could be simple interest. For example, if I start with $100 in an account, and let's say I borrow money from you and you charge me 8%, right, every year. So this is simple interest. So I borrow from you 8% interest for 3 years, $100. So the first year I owe you 8% of 100 is $8. The second year I owe you 8% of 100, $8. And the third year, $8. So together, to make it easier, we just make two years, so you don't have to do that much calculations. So in 2 years, how much do I owe you? Well, I still owe you 100 plus what? Plus the interest, which is $16. Now, how do we calculate this? Well, it looks like all I have to do to calculate how much interest every year I have to give you is to take the principal amount I borrowed and multiply it by, after the first year, how much do I owe you? I owe you 108. How do we get 108? We can multiply it by 1 plus the rate in decimal, which is 0.08. And this gives us what? 108. So how do I get 116? Well, we got to multiply again by what? 1 plus, so I don't want to do it here. I can do it over there. So that's 108. So I start with 108 and multiply by 1 plus 0.08 again, right? So it would be, they don't want to do that. So what I have, the second year, you don't want to charge me interest on the top of interest. So what you're going to do to calculate 2 years of interest, you're going to take 100 and charge me for 2 years of that much interest instead of 1 year, right? And you're going to get me what? 100 plus 16% of 100 is 116. So you get the total. So it looks like in order to get the total, we start with the principal, and add whatever interest I owe you after 2 years. You don't stop in the middle and calculate the interest. So it would be the principal plus the interest. But what is the interest that I owe you? Interest would be the principal times the rate and times how many years, right? So that means the value of the money I owe you is P plus PRT. That's the interest, and that's the principal. And if you simplify it, that's just P, factor P out, you get 1 plus RT. So that is the simple interest. Now, in compound interest, this is how it works. It's still $100, and you charge me 8% per year. But what you're going to say is this. You say, okay, after 1 year, you owe me 108, right? But at the beginning of the second year, you owe me 108 and 8% interest on the top of 8% of 108. So what you're going to say is this. You say, I'm going to charge you, right, 1 plus 0.08, right? And I'm going to get 108. Then you're going to say, I'm going to use 108 here and multiply it by 1 plus 0.08 again. Now this time, this amount is going to be more than 108, right? What is 8% of, so let's calculate it here. So what is 8% of 108.08? Is 8.64, so that would be 108.64. So if you add these two, you get 116.64, right? But instead of doing it 1 year at a time, you could just do it this way. 100 times 1 plus what? 0.08, and then to the second power. You just multiply it again, right? Now this becomes an exponential function. This one right here is linear, but this one becomes exponential because we are going to add number, and then the top would be number of years, so the variable is in the exponent position. Okay, so you could also, now that you see you make more money, you can divide the year into 2 and say, okay, you owe me $100 the first 6 months, and I'm going to charge you what? 4% for 6 months, because it's 8% for the whole year, right? So you're going to charge me what? 4% for the 6 months. And you say, okay, you owe me 104, and then at the beginning of the second 6 months, you owe me 104, and you owe me 4% of 104. And what's 4% of 104 is 416. So here, the first year, you owe me 104, right? So let's write just the interest you owe me. I'm just going to charge you I'm going to write the interest here. So you owe me $4 here for the first 6 months. For the second 6 months, you owe me 4.16. And then now the third 6 months, I owe you 108.16, and 4% of that. What's 4% of 108.16? Is 3, let's say 3, round up. So now you owe me how much? I owe you how much? 112, and then 49. And then now 4% of that is what? 4% of 112.49 is 4.49, and let's say 450. Now you're going to add all of these now, right? Which is basically would be 112.49 plus what? 450. That would be 116.99, right? So that's how much I owe you. But before I owed you what? I owed you that much. So that idea caused people to think, okay, what if we divide the year into 3, 4, 10 parts, right? So what's the formula in this case? Well, in this case, the formula will look like this. A equals to the principal amount times, well, is 1 plus, not the interest in decimal, but we have to divide the interest depending on how many partitions we have per year. So we have to divide the interest, we're going to call that maybe n, right? So the n is the number of partition in a year. So if you divide it into 4 parts, n is 4. If you divide it into 365 parts, then that's 365. And notice that this number right here now, if you do it for 4 parts, then we're going to have to do what? We're going to have to multiply 100 by 1 plus 0.08 divided by 2. And then one time we have to multiply to get this number, another time to get this number, another time to get this number, another time to get this number. So that means we have to raise this to what? 4 power. And notice 4 here is really number of years, which is 2, and times the partition per year. In this case, we had only 2 partitions in each year. So each year has 2 periods. We have 2 years, so that's 4. So that would be 4, which is really 2 times 2. So the formula here is number of partitions per year times number of years. This is called compound interest formula, where A is the value of the loan or the money. It could be a saving account, right? You put it in a saving account and they pay you interest. It would be the same thing. Okay? And now that we are added, let's talk about that number E. So a mathematician, and long time ago, several centuries ago, Bernoulli, said, okay, what if I put a unit of money, let's call it $1. What if you put $1 in an account that pays 100% for 1 year, right? How much money are we going to have in the account? So A is going to be the principal again, is what? The principal is $1. And so it would be 1 plus, or in decimal is actually 1, because if you move the decimal 2 places to the right, to the left, you get 1. So it's 1 divided by n, and then to what? To the power of n times t, which is just n, right? So we get that. So what you get out of this situation is depending on how many divisions you have in a year. So if you have just 1 year, you don't divide it into any parts, n equals to 1, so you just get 1 times 1 plus 1 is 2, so you get $2. So if n equals to 1, you get $2. Now if n equals to 2, then it would be 1/2, so it would be 1 plus 1.5, and 1.5 to the power of what? 2. So what would that be? Well, to make it easy, Bernoulli didn't have calculator, but we do. So what we can do is we can put this formula that we have, which is this one right here, we put it in y1. So we can put parentheses 1 plus parentheses 1 divided by, instead of n, I just put what? I put x. Then close parentheses, and I'm going to raise it to the x power. And then I go to, I go to second table set, and I'm going to change that to ask. It's already on ask, so I'm just going to leave it like that. Then I'm going to go to table, which is right there, second table. Well, the second didn't work, so let me do it again. Second table. Let me erase all that. So if I put 1 time per year, I get $2. If I put 2, I get 2.3. What if I divide it into 12 parts? So every month I charge you. Well, I get 2.6 something. What if I do it, 1,000 times per year? 2.71 something. If I do it 10,000 times, million times. So Bernoulli noticed that no matter how big this n is, the value of a would be limited to this number. And this number is the famous number called e. So when n goes to infinity, the value of your money goes to, if you have $1 invested, goes to number e, 2.718. And that number is programmed in the calculator, is right here, and also as a function with the base e is right here. You see it right there, e to x. So if you go to second and go to e, see on the screen, press enter, you see the value of that number is 2.718 something. And if you want to raise that number to a number, you could go to here, right here, e to, let me go to e to right there. And then you put a 2, for example, that would be e to second. I'll put c instead of, let me do it again. So e to the second power would be that. All right, so that's the number e. Now we are ready to actually do some problems in this section. So let's see. It says after a certain number of years, the value of an investment account is represented by this. What is the value of account, right? Well, we're going to put that in a calculator and find it. Right? So what do we do? Let's just start from here. So 0.04 divided by 12. 0.04 divided by 12 is that number. So now we have to add 1 to it. So we add 1 to it, enter. Let me do it again. So 0.04 divided by 12. And then we add 1 point something. So we are inside the parentheses now. We have to raise it to 120. So raise to the power of 120. We get that number, and then we have to multiply this number by 10 to 50. So multiply by 10 to 50. There. I put something else. Let me get the last thing. So let me do 0.04 divided by, I keep turning on the alphabet, that's why I get there. So let me add 1 to it and raise it to 120. And now we want to multiply that, right, by 10 to 50, and we get that, 15280.03. So that's how much money is going to be in the account. Now it says, what was the initial deposit made to the account in the previous exercise? So initial amount is what again? Initial amount is what you start with, right? So what you started with here was 10 to 50. And now, how many years had the account from previous exercise been accumulating interest? Well, remember in the formula, so let's answer that question here. So how many years had the account from the previous exercise has been accumulating interest? Well, we know this number right here, this is actually NT. Now we know N is 12, so that means 12 times number of years has to be 120, so T has to be 10 years, right? All right, the next question. An account is opened with an initial deposit of $6,500. So let's do that problem. Let's do number 31. It says an account is opened with an initial deposit of $6,500 and earns 3.6% interest, compounded semi-annually. What will the account be worth in 20 years? Okay, so before we answer this question, we have to have a formula for this, right? So we know the formula is A equals to P times 1 plus 1 over N, and then NT. Now it says initial amounts of 6,500, so that means we start with 6,500, and 1 plus, this is not 1, that's R, sorry about that. That's R over N, not 1. Okay, so 6,500 and earns 3.6% interest compounded semi-annually. So compounded semi means twice a year, so N is 2, and R is 3.6%, so you have to move the decimal 2 places to the left, so it's that. So that would be 0.036. And then N here is number of times the year is divided into, which is 2 partitions, so that's 2, and then T, right? So that is the formula for this situation here. Now, it says, what will the account be worth in 20 years? Well, we just have to substitute 20 for what? For T. So the question here that you're asked to solve is, what is A of 20? See, we write A, but really A is a function of T and is an exponential function, right? So A20 is 6,500, 1 plus 0.036 over 2, and 2 times what? 20. So we are going to again use the calculator. And so we start from inside. We can actually put the whole thing in the calculator in one statement. So 60, so you can put 6,500, right? And put parentheses, 1 plus parentheses for 0.036 divided by 2, parentheses closed twice, to the power of 2 times 20 is 40. And 40. There. In one step, you can do all the calculations here. So we're going to have $13,268.58 in the account, right? So that is the idea of using compound interest. Let's do 36. It says use properties of rational exponents to solve the compound interest formula for R. So what we want to do is we want to, let me go up a little bit here. So we want to solve this for R, right? So let's write it this way. A equals to P times 1 plus R over N to NT. So what we want to do, we want to get this R out of here and put it on one side by itself. So you have to get rid of all the stuff around it and below it, right? So we're going to start with p. The first thing we need to get rid of is p, so we divide both sides by what? By p. So we end up with 1 plus r over n to nt power. Then we have to get rid of nt power. Now, to get rid of nt power, we use this idea that a to mth power and then to n power is what? Is a to mn, right? So, and also we know that if we have, so this n, mn, that's what it means. You multiply the exponents. Now, if I have, let's say, x equal x squared Now, if I have x squared equals to, let's say, 4, and I want to solve it, what we say is take a square root of both sides. But taking a square root of both sides is equivalent to what? To raising it to 1/2, right? Because raising to 1/2 is like a square root. And notice that 1/2 times 2 is what? Is 1, so it's x to the first power equals to square root of 4, of course, right? Now, we know that if we take even root, of course, we have to put plus and minus. So x to the first power equals to that, so that's plus or minus 2. Now here, in order to get rid of this nt, we have to raise to a power of what? To a power that if we raise nt to that power, we get 1. So what times nt gives you 1? Well, 1 over nt, right? And it cancels, so we get 1. So we put 1 over nt here. And then the same thing on this side. A over p has to be to the power of what? 1 over nt. So this goes away, obviously, is 1. So what we end up having here is, let me put it here quickly, is that on the right hand side we just get 1 plus r over n. On the left hand side we have a over p to 1 over nt. And now you move the 1 to this side, so you get a over p 1 over nt minus 1 equals to r over n. And then now you multiply both sides by n to get what? To get r by itself. So now we got r by itself on one side. That's the expression. Now if you have information about the account, then you can find the interest rate, right? Somebody says that, there was an account that I put, 1,000 in there, and after, 10 years I got, $5,000, and it was compounded, let's say 3 times per year. Then you can put those numbers here and find the interest rate for the account, right? All right, and now we are going to do, let's say, so for the following exercise, determine whether the equation represents continuous growth decay. Now, what is continuous growth? Well, we talked about compound interest, so we're going to talk about continuous interest. So remember I talked about what Bernoulli did, right? So Bernoulli figured out that the expression 1 plus 1 over n goes to e when n goes to what? Infinity. Now if you apply that idea to a equals to p times 1 plus 1 over n to nt, right? I mean, this is r, not 1. Keep putting 1. That expression goes to e if it has a 1. Of course, in the formula we have r. What happens if you apply this to this, and is in the text, so I'm not going to do it here, but you can read it in the text. You end up with P, and then this whole thing, you can put E to RT here, okay? So basically it's like you're switching, you put an R there and you get that expression out of it. So you have to change a variable here. For example, you want this R to be 1, so you can write N as M times R. So everywhere you see N, you put A times M times R. So let me do that now that I talked about it. So that would be R over, instead of N, I put MR. And here we put MR for T. See? MR for N, and then MR for N here. And there's a T still there. And this is R, right? Okay, now, this R cancels, so what we get is P times 1 plus 1 over M, and that's just MRT. And remember we said that if you have two powers, you can separate them, and you can write this as 1 plus 1 over M to the nth power, and then take all of these and raise it to RT. Now when N goes to infinity, also N goes to infinity, because remember they're related here, right? So if M goes to infinity, N goes to infinity, and this whole thing inside the parentheses will go to E. So the formula becomes, right, becomes A equals to P times E to RT. And that's called the continuous interest formula. And that's what we have here, right? Is this continuous interest formula? Yes. Initial amount is 3742, and the rate of growth here is, of course, this is not continuous growth, this is continuous decay, because when the rate is positive, is growth. So this is growth, and let's say if I can find one that is negative, this one. So this one, the growth rate is negative, so it's going to be a decay. This one, T is in the denominator, so it's not growth or decay, right? This one is continuous growth. This one is continuous decay, right? So when we have it in this form, it doesn't have to be used with money. It could be used for any situation that things grow exponentially or decay exponentially. So here, people also like to write it this way: y equals to a. So they write it this way. They can write it like y equals to y sub 0, and then e to kt. Sometimes you see it like that. Or you can see it like a of t equals to a sub 0, and then e to kt. Right? You might see these forms of the same thing. So here, a sub 0 is the initial amount, and a of t is the future amount. So if k is negative, you get exponential decay, and if k is positive, you get exponential growth. So in this case, it's growth. This is not exponential growth or decay, and the last one is exponential decay. All right? So we can do, let's say, number 45 here. Here's an exponential function. We are supposed to find f of negative 1. Now, there are two ways to do that, and that's the last thing I want to do in this video, and then I'm going to do another video So this one requires a bunch of explanations, so it took a little bit longer, but that's okay. So this is the function. So there are two ways to do that. You could just do it on the calculator this way. You could just substitute -1 for x this way. You go to y equals 2. You put the function -4 to the power of, right? And then put parentheses 2x plus 3 and parentheses close, right? Now notice that this negative is not you're not exponentiating the negative, you're exponentiating only 4. So don't put -4 in parentheses here. Should be negative, should not be inside the parentheses. This is the way it's supposed to be. And again, we go to second, right? And then table set, make sure, second table set, make sure this says ask here. And then go to second and go to table, second table. Let me turn it off, second table, right here. So I'm gonna delete all that and put what? Put -1, which is -4. But that's how you do it with the calculator. Now, of course, you could do it by hand, right? How do we do it by hand? Well, by hand, you say, what is f of -1? That's -4 to the power of 2 times -1 plus 3, right? Which is -4 to what power? 2 times -1 is -2 plus 3 is 1. So that's -4. You can do it by hand. Okay? So in the next video, I'm going to talk about, let me come back here and say bye to you. So take care of yourself, and I see you in the next video on 6.2 and 6.3 and the rest of them. Take care.